Hello students. So welcome to this particular lecture. So continuing on to the skewed gates. So this particular example on this particular slide talks about the two input NOR gate, and we have the unskewed gate, and then the high skew gate, and then the low skew gate, and would like to go through how to evaluate the logical efforts and then the parasitic normalized parasitics for this different skewed two input NOT gates. So unskewed gate, it is quite common. It is 5 by 3 and 5 by 3, and then the normalized parasitic is anyways 2. The logical effort is 5 by 3. That's what I have written here. For the high skew gate, let me pick up a pointer. So now the widths of the transistors are 4, and then on the NMOS side it is 0.5, on the PMOS side it is 4. So my benchmark inverter will change for the pull-up circuit and then the pull-down circuit. So the benchmark inverter for the pull-up circuit will be 2:1. The reason is it's equivalent of the two transistors on the PMOS side will give me effective transistor width, the equivalent transistor width of 2. And that's the reason why I need a 2:1 inverter as the benchmark inverter for the pull-up side of the circuit. For the pull down side, 0.5 is the width of the transistors, and that's why my benchmark inverter will be 1:0.5. So with this particular benchmark inverter, can we now calculate what is the logical efforts and what is the normalized parasitics? For the going up output, the logical effort is nothing but 4 plus 0.5 divided by 2 plus 1, that will be 3, so 3 by 2. The normalized parasitic for going up will be the almost 2 plus 1 will come on to the denominator side. On the numerator side, it will be 0.5 plus 0.5 plus 4. That is the output capacitance seen at the the capacitance seen at the output node. So that will be 5, and then the benchmark inverter will show a capacitance of 3 at the output node. Hope this is clear. For the logical effort for the output going down, it will be 4 plus 0.5 divided by 1 plus 0.5 turns out to be 4.5 divided by 1.5. The parasitics for the going down output will be nothing but 4, the 4 plus 0.5 plus 0.5, so it will be 5 divided by 1 plus 0.5. So it turns out to be 10 by 3, and its average average of GU and GD will give me the logical effort average 2.25. And the normalized parasitic average here is 5 by 3 and then 10 by 3, and that's average, which will give me 5 by 2. All right, hope this is clear. If I look into this 5 by 3, which is almost 1.66, this particular value, and then compare with that of 2.25, this is quite large. So the G average is quite large. Although this 3 by 2 turns out to be less than 1.66 for an unskewed inverter. So if we can characterize the NOR gates in such a way that the output is always going up more frequently, then I think we can have this the high skew NOR gate for the going up output. For the low skew two input NOR gate, it turns out to be very, very interesting. So the size of the low skew two input NOR gate, so it is a low skew, that means that the NMOS should be more dominant. So the NMOS is of size 1. Here in the high skew, we wanted the PMOS to be more dominant. So we had the same size as that of the unskew 1, 4 and 4, and then made the NMOS size lower. And that's why it became high skew two input NOR gate. In the low skew version, if it is this 1 and 1 is taken from the unskewed two input NOR gate of 1 and 1 size. So 1 and 1 is what we have. And to make it low skew, so in this particular circuit, what we have done is on the PMOS side, the strength has been reduced, the width has been reduced. And the NMOS side, the width is taken as same as that of the unskew, and thereby it becomes a low skew. Low skew in the sense the NMOS transistor is more dominant now. So if I have this particular sizes, my benchmark inverter for the going up output and then the going down output will be different. So the inverters, benchmark inverter for the going up output will be nothing but 1:0.5, and for the going down will be nothing but 2:1 inverter. right? Because this size is 1 here, that's why my inverter's NMOS size should be 1, and thereby my PMOS benchmark inverter will be 2 here. For in this particular case, the equivalent, the transistor for the 2 of these transistors in series will turn out to be the size of 1, and that's why we have the benchmark inverter size as 1 on the PMOS side, and thereby the NMOS side benchmark inverter size will be 0.5. So hope this is clear. Now if I have this particular benchmark inverter sizes, the logical efforts for going up will be nothing but 2 plus 1, that is 3, divided by 1 plus 0.5, which will be 1.5, turns out to be 2. The parasitics for going up will be nothing but whatever is the output capacitance seen in this particular output node, which will be 2 plus 1 plus 1, 4 divided by 1.5, so it will be 8 by 3. For the going down output, the logical effort for the going down output, which will be nothing but 2 plus 1, that is the input capacitance, divided by 2 plus 1, the benchmark inverter, turns out to be 1. And the parasitics will be the output capacitance, the capacitance seen at the output node, which will be 2 plus 1, which will be 4, divided by the benchmark inverter 2:1's output capacitance, which will be 3. The average of GU and GD turns out to be 1.5, and then the P average turns out to be 2. And now if I start comparing between the unskewed 2-input NOR gate and a low-skew 2-input NOR gate, turns out that the low-skew on an average also it is 1.5, which is less than 1.66, which is 5 by 3. Parasitic average turns out to be the same. P average is 2 here, P average is 2 here. Right, so the parasitics remains the same. The logical effort, there is an advantage for the low-skew 2-input NOR gate, because the logical effort is less than that of the logical effort of an unskewed 2-input NOR gate. So this becomes kind of a very important circuit, and in most of the memory designs, we will have to use the 2-input NOR gates or whatever, multiple inputs NOR gate. In that case, it is always preferred to have a low-skew 2-input NOR gate, just because this logical effort is less, and thereby my overall delay will be less. Alright, hope this is clear to everyone. Moving forward. Now, so what we had seen is for a 2-input NAND gate and for a 2-input NOR gate, we realized that the logical effort for a 2-input NOR gate turns out to be best for a low-skew 2-input NOR gate. Whereas for a NAND gate, so let me go back to the NAND gate. For a NAND gate, we noticed that the logical effort and then the the parasitic average parasitics turns out to be best for the unskewed one compared to the other gates. So what it really means is somewhere the skewing will help me to reduce the overall delay. So can we now find out the optimized width for the standalone gates, which will give us the lowest delay? Right, so moving in that particular direction, let's say that I have this unskewed 2-input NOR gate, and here is a low-skew 2-input NOR gate, and I try to find out the overall delay. And this time we will try to apply the Elmore delay, because that turns out to be more accurate than that of the linear delay model. So if I use the Elmore delay method, I need to use the internode diffusion capacitance, and that's why it has been reflected here. So for an unskewed 2-input NOR gate, I have the sizes of 4 and 4 and 1 and 1. At the output side, I will see the capacitance of 6C. In this particular internode diffusion capacitance, it is having a 4C. And if I want to find out the overall delay, I need to find out the propagation delay falling and then the rising, and then total it up and then find out the average. Although I'm not, average is nothing but total divided by 2, but that is something I have just ignored it, because it will be nothing but linearly scaled by 0.5 times, right? So I'm just calculating the overall total delay, which is nothing but the propagation delay falling and then rising. The propagation delay falling will be nothing but 6C capacitance in this particular node, and it is a falling output. So one of them should be on. So it will see a switching resistance of R. So 6C into R, and then this 4C is also there, but the shared resistance turns out to be the R value. So it will be 6C plus 4C into R, turns out to be 10RC. Propagation delay rising will be nothing but, so both of this should be on, and individual one of the transistors has a switching resistance of R by 2. So overall switching resistance will be R. So 4C multiplied by R by 2 here, and then 6C multiplied by total R will give me the propagation delay rising. So 6C into R plus 4C into R by 2, 8 RC. So the total delay turns out to be 18 RC. And if I try to find out for the low skew two input NOR gate, the internal diffusion capacitance is 2C. The output node total capacitance is 4C, because my sizes are 2, 2, 1, 1. And if I want to find out the propagation delay falling, this one of this transistor should be on. So 4C multiplied by R plus 2C multiplied by the shared resistance will be R. So it is 6 RC on the falling side. On the rising side, it will be nothing but 4C multiplied by the switching resistance here will be R, the switching resistance here will be R, right? A size of 2 on the PMOS side will give me a switching resistance of R. So 4C multiplied by 2R and then 2C multiplied by R, so which will give me a total of 6 RC. 6 plus 6, total of 4C into 2RC, correct. 4C into 2R plus 2C into R. So it will be 10 RC. So the total delay will be nothing but 16 RC, which is actually less than the 18 RC. So that's what we had actually calculated, or we had noticed in the previous slide when we calculate the logical effort, right? So logical effort, although it will be used for the next stage, what it says is overall that particular stage has somewhere the delay is less. So if I want to find out the best sizes, right, so that my overall delay, the total delay in the sense the propagation delay falling and then the propagation delay rising, the sum of it should be less. If that is the case, I need to identify what is the best size. So moving ahead, so if I want to find out the best size, or in fact I will go ahead and say that it is the best size ratio, the best P by N ratio, if I want to find out that, then I will have to use the Elmore delay method, find out the total delay, that is nothing but the propagation delay falling and rising. We'll get the total delay expression in terms of a variable. And then if I do a derivative of that and equate it to 0, I should be able to find out the best optimal sizes. So what in this particular case, what I've done is for a 2-input NOR gate, I've taken a variable P on the PMOS side. So P represents the width of the PMOS transistor in this particular case. And there are 2 PMOS transistors for the 2-input NOR gate. And for the NMOS side, I've taken a size of 1. So my overall capacitance and then the resistance, I now have to represent it in the form of the variable P. So my overall capacitance is, the diffusion capacitance is PC here, because it will have a, the shared diffusion capacitance, shared diffusions, which will give me the capacitance of PC. The output node capacitance reflected at the output side will be nothing but P plus 1 plus 1, so P plus 2 into C. The switching resistance for this particular transistor will be 2R by P. The switching resistance of this particular transistor will be again 2R by P. The switching resistance of this transistor is nothing but R, and either one of them, right? And now I should be ready to evaluate the expression of the propagation delay falling and then rising. So the propagation delay falling in this case will be nothing but P plus 2 into C multiplied by R plus PC multiplied by the shared resistance of R. And so overall the propagation delay falling in terms of P will be nothing but 2P plus 2 into R, into RC. Propagation delay rising in this particular case will be nothing but P plus 2 into C multiplied by 4R by P, right? Propagation delay rising, it will be nothing but P plus Q C into 4R by P. So this is this particular, the expression. The other one is this PC multiplied by 2R into P. So PC into 2R by P. So that is this particular expression. Right, so I will get this TPDR and TPDF, and if I do the summation, I will get the total delay in terms of the variable P. So this is my overall expression for the total delay. We need the best P by N ratio. We need the best P here because the other N side I have taken the width as 1. So if I do a derivative with respect to p and then equate it to 0, I should be able to find out the p value. And if I do that, the derivative of this total delay with respect to p, 2p derivative will be nothing but 2, this will be 0, and this one will be 0 here because p and p gets cancelled, and it will be minus 8 by p square. So if I take the derivative of this total expression. So finally, I will have this particular equation. What it means is the p should be of the value plus or negative 2. We cannot have a negative value in the widths. So we will take the positive value. So this will be my final expression, which says that p by n ratio should be of 2:1 ratio for the 2-input NOR gate. Right. So what it really means is if I take the size of 2 and then 1 here, it will give me the best delay. Right. I can also take the size of 4 here. Size of 4 here. I can take the size of 2 here and then the size of 2 here. It will also give me the similar delay. So similar total delay. So this is also p 4:2 or 2:1 or 8:4. Everything should give me the best delay. Right, the best total delay in terms of the standalone circuit. Right, so if I want to find out the best p by n ratio for the 2-input NOR gate or for any that matter 2-input NAND gates or an inverter, I need to find out the total delay expression, then take the derivative with respect to one of the variables, p variables, and then equate it to 0, and then we should be able to get that best p by n ratio. Right, so for the 2-input NOR gate turns out to be 2:1 ratio. So similarly, can we find out for the 2-input NAND gate, what is the best ratio? For the 2-input NAND gate, I have taken on the NMOS side the size of 2, and on the PMOS side I have taken the variable p here. So which means that the p should be the PMOS width. On the NMOS side, it is nothing but the variable 2. So if I have this, the total capacitance seen at the output node will be nothing but p plus 2, which will be 2p plus 2 capacitance. And in this particular inter-node diffusion capacitance, it will be 2C. So the total propagation delay falling in this particular case will be nothing but 2p plus 2 into C. This particular capacitance value multiplied by, so this will have a switching resistance of R by 2. This will have a switching resistance of R by 2. This should have a switching resistance of 2R by P. And of course, this one should also have the switching resistance of 2R by P. So if I have this switching resistance, then I should be able to find out what is the propagation delay falling, and it turns out to be 2p plus 2 into C into multiplied by R plus this particular capacitance 2C multiplied by R by 2. So that will be my propagation delay falling. Propagation delay rising will be nothing but 2p plus 2 into C multiplied by 2R into P, and finally this 2C multiplied by the shared resistance of 2R by P. So the total expression turns out to be this, which is nothing but 2p plus 7 plus 8 by p multiplied by rc. And if I take the derivative of this particular expression with respect to p, it will be 2 minus of 8 by p square. So p turns out to be, the best p turns out to be 2. So the best p by n ratio for even for the 2-input NAND gate is actually 2:2. Right, because the best p turned out to be the value 2, and n we have considered it to be 2. So the best p by n ratio turns out to be 2:2 or 1:1. Right, and if you remember our for the 2-input NAND gate, the unskewed inverter, the unskewed 2-input NAND gate, the unskewed configuration had the PMOS width of 2 and NMOS width of 2, which was giving the best logical effort and the best parasitics. All right, across the different high skew and low skews. Hope this is clear. How do we evaluate the best p by n ratio? All right, so this is an empty slide. So what we had up till now, what we had done was for the 2-input NAND gate, the best p by n ratio, so I'm going to write it as best p by n ratio, turns out to be 2 and 2. For the 2-input NOR gate, the best p by n ratio turned out to be 2:1. Right? So this is the best, so I'm going to write it somewhere that this is the best p by n ratios. All right. Now, if I want to do an unskewed one, For the 2-input NAND gate, for an unskewed gate, for a 2-input NAND gate, it is actually 4:1 ratio. Right? On the PMOS side, I need to have the size of 4 because, sorry, this is 2-input NAND gate. So I will just erase it. Uh, yeah. Right. So for the 2-input NAND gate, it was the size of 2:2. For the 2-input NOR gate, it is the size of 4 on the PMOS side and then 1 on the NMOS side. Right? For a 2-input NAND gate, it is actually 2:2, right? Which is actually nothing but here I can say that it is 1:1. I'll come to that. And this is 2:2 for an unskewed one. The size of 2 is required on the NMOS side to get to get to the falling resistance MZ of the benchmark inverter, and the size of the PMOS side 2 is there for the 2-input NAND gate, because either of the branch will be on, and then I'll have the rising resistance equal to that of the 2:1 inverters, benchmark inverters. So once I have this unskewed form, right, which is considered from making the equal rise time or the equal falling time. So here, if I have the size of 2 and 2, I will have the same the falling resistance and then the rising resistance. So I'm going to write it as the rising resistance and then the falling resistance turns out to be R, right? And it matches with that of the 2:1 inverter. Similarly here, 4:1, I have taken this sizes such that again the rising resistance and then the falling resistance matches with that of, it should be equal to that of the R, and it also matches with that of the 2:1 inverter. So in that case, if I have an unskewed version, right, I should be able to get to the best P by N ratio. Right, I can do that if I have an unskewed version, and if I take the square root of the unskewed version of the P by N ratio, right, then this one should be able to give me the P by N ratio. In fact, I'm going to write it as the best P by N ratio. Right, so let's try to validate this. If I actually have an unskewed version of the P by N ratio, which is nothing but 2/2 for the 2-input NAND gate and 4/1 for the 2-input NOR gate, if I take the square root of that 2/2, it will give me the square root of this, the output of the square root of P by N for an unskewed version will give me 1:1, which is what I have written here, the 1:1. Similarly, for the 2-input NOR gate, the unskewed 2-input NOR gate gives me 4:1. And if I take the square root of that here, 4:1, which will give me 2:1, and that is what we get here, 2:1. All right, hope this is clear. So to generalize, so the best P by N ratio, it is actually the width for the equal rise delay or the fall delay with respect to the 2:1 inverter, right? So in another sense, if I have an unskewed version of the gates, whatever it could be, a 2-input NOR gate or an N-input NOR gate or a 2-input NAND gate or any other combinational gates, if I can form the unskewed gate, right, the unskewed gate formation is very, very simple. I need to make sure that the falling resistance and then the rising resistance matches with that of the 2:1 inverter. And if I can get that, the square root of the width of those particular inputs, right, where the inputs connected to the PMOS and the inputs connected to the NMOS, if I can identify what is the square root of that width, that square root and the output of the square root should give me the best P by N ratio. So the best P by N ratio for actually 2:1 inverter, which is an unskewed inverter, turns out to be the square root of 2:1, which is again a low skew inverter, right? Because the low skew, because this size, it is become less than that of 2, and thereby the PMOS is going to, or rather the NMOS is going to be more dominant. Right, again for a 2-input NAND gate, I have taken an expression 2:2. So the best P by N ratio is nothing but the square root of 2:2, which is 1:1, which is again an unskewed, for a 2-input NAND gate. right? The best p-band ratio for a two-input NOR gate is nothing but 2:1, which is again a low skew. So for inverter and then for the NOR gate turns out to be the low skew version, which is better in terms of the overall delay. Whereas for the two-input NAND gate, unskewed version is better in terms of the overall delay.